Hello, I'll talk today about corporate social responsibility via multi-armed bandits. This is joint work with Tom Ron and Onno Ben-Porat. So our motivation is the following problem. Let's say a company wants to publish a job ad online and wants to optimize its campaign based on the cost per click. Now, it is already established that women have higher cost per click than men for advertisements for STEM positions. So that might mean that women might be less exposed to information about STEM career opportunities. Therefore, they may never apply to such jobs. So if a company wants to act fairly and display ads to all the subpopulations, the company might need to sacrifice part of its short-term utility and pay a higher cost per click. So our work is about quantifying this trade-off of maybe paying a short-term higher price in order to achieve some long-term goal that the company or the user deems as something they want. We frame this through the notion of corporate social responsibility, which is a self-regulation act of philanthropic responsibility, which many companies have lately been taking upon themselves. So, for example, last year, Starbucks announced that it helped more than 4,500 employees earn their bachelor's degrees. Microsoft spent billions of dollars with minority, disabled, veteran, LGBTQ, and women-owned businesses. So this framework exists in which companies spend money to achieve these longer-term goals, which they deem worthy, and we want to tie this to their actions in the short term. And specifically, we frame this problem as a multi-armed bandit. So I assume most of you are familiar with that. Just very shortly, it's a multi-armed bandit. MAB is a sequential decision-making process. So each round, the decision maker pulls an arm and obtains a reward. And the goal is to maximize the decision maker's cumulative reward. And specifically, we think about, for example, displaying an ad, choosing to which population, for example, women or men, an ad should be displayed as a pull on in the multi-armed bandit as a playing in a single round. And more formally, we call this the reward opportunity MAB model, ROMAB. And we will have K arms, which correspond to K subpopulations, T time steps. RT will be the reward obtained in round T. N subindex IT will be the number of times RI was pulled by the end of round T. We'll use mu to denote the reward vector. So it's a vector of dimension k. So each arm has its true reward. And mu star will be the maximal reward. So that is the best arm. So in standard multi-armed bandits, what you'd like to do, if possible, is just to pull the arm I, which corresponds to mu star. Delta I is the reward gap. So it's mu star minus mu I. And F is something which we'll explain shortly, but that will be the fairness function. So it's a function from the k-dimensional hypercube to the k-dimensional hypercube. And this will encode this notion of, oh, we need to pay more, for example, to present this ad, but how much more, right? So this might not necessarily be linear, and it is a function of the reward. So maybe if an arm has a very low reward, so ordinarily I would never pull it, I might deem it fair not to pull it because just the cost to the company is so high. And lambda would be the transfer cost, which again we will explain shortly. So what is this fairness function? So first it's a function which takes as input this vector of possible rewards, which we assume are bounded between 0 and 1. And we assume that the sum of these, of the fairness constraints is as at most 1. We assume that it's a Lipschitz function. So if for two similar reward functions, mu and mu prime, the fairness should be similar up to a factor of L, which is the Lipschitz constant with respect to the L1 norm. And just what could be examples of fairness functions? So have the uniform fairness function, which says, basically, every subpopulation should get at least a fixed fraction of opportunities. Let's say we should pull each arm at least 5% of the times, no matter what. So that is a very simple fairness function, which ignores completely the rewards, mu. We have a linear fairness function, which is, let's say, mu I over k. The higher the reward for the arm, the more I am inclined to pull it, or put another way, if an arm has zero reward, for example, I might not be forced to pull it at all. You could have a softmax fairness functions and many more. So within this model, what is the utility? So we define the utility with respect to some algorithm and some finite horizon, capital T, as follows. We have first just the sum of the rewards. That's the standard multi-arm bandit utility. But then we subtract something. We subtract lambda times sum over the arms of the following term. This is the maximum between t times the fairness function of mu at the index I minus nit, either that or zero. So what is this term? It means, let's say nit is 5. So by the end of my horizon, I pulled arm I 5 times. But let's say my fairness function times t says 10. So it tells me, oh, the fair thing to do, given that this arm has reward mu, or that mu is the entire vector of reward, you should have pulled this arm 10 times. But I just pulled it 5 times. So now I pay lambda times 5 per this arm to offset the fact that I was not fair towards arm I. Okay, so that is the CSR kind of component. And lambda codifies my cost. Like, that's why we call it the transfer cost. It's a form of a cost of fairness, right? How much should I pay for not handing out opportunities in the way I deemed fair through the fairness function f. Now, the regret would be kind of in the standard way, the expectation of the optimal algorithm minus the expectation of any algorithm like ALG that I chose to use. And of course, our goal would be to find a way to minimize our regret. Now, in related work, so we, of course, were not the first to look at bandits and fairness and so on. So there's been early work from Joseph et al. About, in 2016, something they called meritocratic fairness, which says that a learning process is considered unfair if an arm with a lower expected reward is favored over an arm with a higher expected reward. We think that sometimes it is actually fair to give opportunities to an arm with a lower expected reward or a higher expected cost for many reasons, societal reasons. Another notion of fairness is calibrated fair policy from Liu et al., which says that a fair policy is if you select arm I with probability equal to the probability that the reward realization of the arm I is the highest. And finally, there's a fair SMAB from Patil et al. From 2019, which is the closest to ours, which says fairness is if you pull each arm at least some predefined minimal number of times. And that actually corresponds exactly to our uniform fairness function. But as I said earlier, that actually ignores the actual rewards, which say, oh, maybe it could be fair to give more or less opportunities depending on the actual reward you expect from that arm. So, okay, so now let's develop our algorithm. So first, let's ask what's the optimal algorithm, the oracle one. So remember that mu, the vector of rewards per arm, is not known to us. Well, let's say we had known it. So the optimal algorithm would be as follows. So define delta I, recall, as the reward gap, mu star, which is the maximal mu minus mu I. And then the optimal algorithm we show is as follows. So for every suboptimal arm I, you should pull it as follows. If delta I is greater than lambda, if the gap is greater than lambda, you should just never pull it. It's always worth it to just pay the transfer cost and never actually pull this arm. If delta I, the gap, is smaller than the transfer cost lambda, then you should pull it t, which is the horizon, times whatever the fairness function tells you for that arm. You should pull it that many times. And if delta I equals exactly lambda, there's like multiple solutions. You could pull it anywhere between 0 and t times f ui. Now, after you did all this, you pull the optimal arm, the remaining pull. So if you you allotted all the opportunities that you needed to. If you have any remaining pools, you should just pull the optimal on. And we know that this is order insensitive, so the optimal algorithm is actually not unique, and which will be important soon. So this is the optimal method, and now we present our algorithm, which of course needs to learn the vector mu on the fly while satisfying all these constraints. And this, we call this the self-regulated utility maximization algorithm. It has 4 phases. I'll explain them quickly. So in the first, so this, we base this off UCB ideas, like the classic upper confidence bound algorithm for multi-armed bandits. So in the first phase, we look at the upper confidence bound and lower confidence bounds we have for the reward gaps for the delta i's. And we basically explore them and approximate the reward gaps up to some a parameter beta, which we'll define later exactly. After we're done with this, we go to the second phase, which is now we need to learn what is f of mu. So I won't go into all the details. It's a bit technical, but basically we want to approximate the value approximate the value of f mu for arms which have low opportunity costs. And because f depends on the entire vector mu, right, because it's the relative rewards that matter, we need every time to pull all the arms so as to improve our estimate of mu. And again, we do this up to some factor alpha. Now, once we're satisfied that we approximately know f of mu, then we know, okay, now we know, oh, this arm should be pulled this many times, this arm should be pulled this many times, and so on. So that's phase 3. We now satisfy, remember, that is, we saw that this is order insensitive, so now we can just satisfy all the fairness constraints in order. Once we're done with that, then we can just invoke any kind of good multi-armed bandit algorithm, for example, UCB, for any remaining rounds if we have any. So that will be the 4th phase. Now, what we can show about this algorithm is as follows. So if we fix alpha and beta, the parameters we use to these values, then we can show that self-regulated utility maximization has the regret, which is O of k to the 5/3, L to the 2/3, T to the 2/3, and then the cube root of log T. And so remember, k is the number of arms, L is the Lipschitz constant of the fairness function, which we assume we know, and T is the horizon. And we can show actually that this is pretty close to a lower bound. So there's, for a fixed T, K, and L, there is an RO MAB instance which has regret at least omega of T to the 2/3. So we're up to log factors close to the lower bound. Okay, so now just to show some experiments, so we set up 6 arms, mu1 through mu6, which are 0.2 to 0.95 and kind of fixed intervals of 0.15. We try 3 transfer costs, the lambda, O, 0.4, and 0.8, 3 different fairness functions, the uniform, linear, and softmax, different horizons, repeat this 200 times, and use indeed UCB1 as the black box algorithm. And what we see is as follows. So on the left, lambda equals 0, so there's actually no fairness constraints, just standard multi-armed bandits. As we increase the transfer cost, we, of course, utility drops. And note that the longer the horizon, the shorter are the exploration rounds that are needed to approximate f of mu. So kind of for longer horizons, we can actually get to higher utilities because we know f of mu and we can spend more rounds and getting higher rewards, while at the same time satisfying the fairness constraints. And another way to look at this is to look at the round distribution of the phases of the algorithm. So recall the algorithm had 4 phases. So on the left-hand side, it just does like standard UCB1 all the time. But for lambda equals 0.4, where the transfer cost, so sorry, if we go to the right-hand side, lambda equals 0.8, almost all the rounds are exploration. That's the blue. So those are the two different types of exploration. And then giving out the opportunities just to satisfy the fairness constraints. In the middle, where we have lambda equals 0.4, when we have a long enough horizon, actually the algorithm gets to phase 4, which is kind of it approximates the deltas well enough. It approximates the f of mu well enough. It allotted all the fairness. It kind of satisfied all the fairness constraints, allotted all the opportunities, and now it is free to run ordinary bandits on the arms, which are actually might be optimal. So that's the kind of brown area around at the top of the horizon equal 2 to the 2 times 10 to the 5th when lambda equals 0.4. So that's in the middle of the slide. And this happens only for the relatively smaller transfer costs, because then it's easier to satisfy the fairness constraint compared to the larger transfer costs on the right. So just to sum up our contribution, we present a multi-arm bandit model, which is balancing between maximizing revenue and this notion of corporate social responsibility. We showed a no-regret algorithm along with a nearly matching lower bound, and we simulated different settings to examine the implications of our model. Thank you very much for your time, and have a great day.